Okay, we have a couple more things to do, and that ends this chapter. Yay! The first thing is about finding the sample size needed if you want a certain margin of error. So that helps you out if you're trying to design an experiment. You wonder how many subjects you need. You want to estimate something, and you have some idea. You're going to use a certain level of confidence for your confidence interval, and you want to be within a certain distance of the true value. And so we want to decide for that margin of error, what n should be. So how do you do that? Well, you take the margin of error, which is z star sigma over root n. So margin of error equal to that quantity, and solve it for n. So we multiply by root n, divide by margin of error, we get that, and then square both sides. Z star sigma over me squared. It's important to use parentheses on that fraction and square the quantity. Otherwise you might square just part of it and you won't get the right answer. As an example, let's find n if the confidence level is 99%, sigma is 0.39, and the margin of error is at most 0.16. So for confidence level 99%, the z star value is 2.576, sigma was 0.39, the margin of error is 0.16. So when we do that calculation, we get 3942. This often happens. It's not a whole number. You've got to decide, do I just round it? What do I do? Do I just take 39? Do I take 40? Does it really matter? Not that much. Either one is going to be pretty close. But we know as you increase the sample size, the margin of error goes down. So if we took something less than this number, the margin of error will just be a little bit bigger than 0.16. Of course, that's not a real thing that can happen. But the number 39 is a real thing that's smaller than that. And the formula will say then that if we solve for the margin of error using 39, it's going to be somewhat larger than 0.16, and if we use 40, it'll be somewhat less than the 0.16. So in this situation where we want a certain margin of error, we really want to mean let's make the margin of error at most that big. Then no matter what we get for n, if it's not a whole number, we always take the next larger whole number. So here, even though it's 3942, which is closer to 39 than 40, we need to use 40 to get the margin of error below 0.16. 39 will put the margin of error just a little bit above 0.16. Okay, and on the other side of the board here, we're going to use a 95% confidence interval to do some hypothesis testing. Hypothesis testing is whether a certain value of mu is possible based on the data. So here we're testing mu is 2500 milliamp hours for batteries. We assume the sigma is 50, and we take a sample of 560 and get a sample mean of 2550. And then go ahead and compute a 95% confidence interval. That's the usual one. So it's x bar plus or minus z star, sigma over root n. Sigma is 50, n is 60. We get this interval here. So we think the population mean, that means the average capacity of this brand of battery, is between 2537 and 2562. The interval does not contain 2500. It's always above 2500. So we're thinking the batteries are actually averaging slightly higher than advertised. That's great. Ordinarily, that's not what goes on. Ordinarily, they advertise something and the battery capacity is slightly less. So it's a pretty honest company saying our batteries average 2500 milliamp hours when really they make sure it's a little bit better. That'd be the right way to do things. Just like mileage on tires, you'd want to just have the mileage be slightly higher than quoted, not slightly less. We said here everything that we need to set up the interval except for the normal distribution of the population. So we have to figure out, are we allowed to do that without checking the population's distribution? Down here it says here, we do not need the distribution of capacities to be normal. That's because we have a large sample. Oh, n is bigger than 40. It's 60. For large samples, x bar has a normal distribution. And so all the calculations we do to create confidence intervals make sense. So it's approximately normal. If the distribution of batteries was really not normal at all, it'd still be approximately normal, but probably battery distributions are sort of normal looking. And so x bar will be very close to normal because the sample size is so large. And the approximately normal is based on the central limit theorem saying the sample mean has a normal distribution for large n. Okay, that ends chapter 16. Hooray! And let's move on to bigger and better things shortly.